Hello and welcome back to STEM Online Academy. My name is Jason Masterakos, and we're going to get right to it. Okay, so today we're going to be looking at why this integral converges only if you spot an interesting exponential trap here. Okay, so most students see this integral right here, okay, and think the hard part is the cosine. Right? But that is not the real trap. The real trap is the exponent alpha that I have here. And highlight alpha. Okay, that's the real trap. Because it actually is going to depend on the value of alpha, right? Alpha is arbitrary. We don't know what alpha is. So depending on the value of alpha, the expression inside the cosine is going to behave differently, right? In a completely different manner. Okay, so that's what I want you to get here. The alpha is important. They're going to behave, the cosine is going to behave in a completely different way, different ways near zero, right? So who knows when alpha, right? So maybe over here, right? Depending if alpha is approaching zero, okay? Whether it's from left to the right, may have different things going on here, okay? Sometimes it goes to zero, right? Alpha goes to zero. And sometimes it will stay fixed, okay? And sometimes it may just blow up. But at that one difference completely is going to change whether the integral converges or diverges. Okay, so depending on alpha, right, what we do with it, if we do things correctly, it's going to depend whether the integral is going to converge or diverge. Okay, and this is exactly the kind of calculus exam problem where students, right, know the Taylor series. Okay, they know improper integrals, whatever, right? So you already heard about that. And still get stuck because they do not know what to do for what to check first. Okay. So you have to be able to combine multiple different ideas and concepts together and be able to deduce things. Right. And that's what my channel is about. It's about helping you solve hard problems like this logically. Okay. So let's get right to it. Okay, so today we're going to solve this using my usual system. For those of you who don't know, for those of you who do know me, my usual system is this. Okay, so let me just write down here. Okay, my usual system is always, here's my system for solving problems. Visualize. Okay, so you're going to visualize first, right? And then you're going to model. Step one is visualize, step two is model. Here's a model. You're going to execute. Okay, so execute. Okay, and then you're going to verify. So this is a step-by-step logical way to deduce how to do a mathematical problem. Okay. So here's the problem, right? So for every, I put it over here, right? For every alpha belonging to R, alpha some constant, belonging to the real numbers, determine all alpha for which the integral, right? My integral I as a function of alpha is equal to the integral from 0 to 1, right? 0 to 1 of 1 minus cosine of x all to the power of alpha. So cosine as a function of x all to the power of alpha, okay? With respect to x all over x to the 3 halves, okay? So we're given an improper integral, right? From 0 to 1. It is an improper integral. Don't think improper integrals are only from have bounds of infinity. This one's from improper because it blows up. That's why it's an improper integral, right? It blows up because of the singularity at the bottom here. So it's an improper integral, right? That's the reason why it blows up. So it's improper. Now, the integrand has a cosine expression in the numerator and a power of x in the denominator, right? So we look here. So 1 second. Here, okay, we have a power of x in the denominator, right? So that's why it blows up. Now, the parameter or the constant is alpha, right? Right over here. That's my little alpha raised to the power of alpha. And it can only be any real number, okay? Because the question said for all alpha in the reals, right? It can be any real number. So our goal is to determine exactly what alpha values make this integral converge. So what alpha values are going to make the integral converge? Okay, what alpha? So let's see what we can deduce here. So this is not just an integration problem, as you can see, right? Well, sure it is. We got a fancy integral here, looks cool and whatever. It's not just an integration problem, it is a convergence problem. Actually, a convergence, I want to be precise because as mathematicians, we need to be precise. It is a convergence classification problem, right? We have to classify what type of convergence it is, right? So we're not just trying to find a nice antiderivative. That's basic, right? Well, not always. They can get complicated, but it would be basic just to ask for how to integrate the problem, and that's it. In this sense, anyways. Okay, to find a nice antiderivative. We are trying to find the main point of the problem is. What do you think the main point of this problem is? Trying to find the exact point where the behavior changes, right? Where this behavior changes of this integrand inside here. Okay. Integrand in here. See where that behavior is changing. Okay. That point is our threshold, you can say. All right. Now, let's move to the main struggle that most students will have. A majority, a high percentage of students will have trouble with this. Regardless, for those of you who think that you're very good at calculus, I can guarantee you, you've been pretty much spoon-fed in your calculus classes. You met a problem like this. Okay? No offense, of course. Anyways, here's where our students are going to really freeze up. Okay? So they see this cosine right here, right? They see the cosine function here. Okay? They see that cosine function, and they immediately think, oh, I know what to do. They either think one of two things. I FOIL in my integral right away, right? And I'm going to just integrate directly, okay? Whatever I know, whatever integration technique I know, and voila. Or I'm just going to use, there's another possibility to use, they multiply in this integral, okay? So they will multiply in here, like FOIL it out, multiply in. And they notice that cosine there, and they say, maybe I should use a Taylor/Maclaurin expansion for cosine, right? That instinct is not wrong. You're on the right track. If you thought of number two, placing the cosine with a Maclaurin expansion for cosine. It's not wrong, but it's still incomplete. Okay? It's incomplete. Because Taylor series only helps when the argument of the cosine is getting close to zero. Okay, so for those of you who don't know, let me go to another page here. You should know this, taking calculus, right? So Taylor, I'm going to put a Taylor expansion. Taylor, let's put here. Yeah, Taylor series. Just to remind yourselves, Taylor series. Okay, for cosine. All right, so cosine, just to remind you, cosine of x is equal to the infinite series sum from n equals 0 to infinity of x to the 2n all times -1 to the n. Let's not forget that. I'll make this better. Like, why am I writing this better? Sorry about that, guys. -1 to the n times x to the 2n all over 2n all factorial. Okay? This should be ringing some bells here. Okay? That is a cosine Taylor series. Right? So because Taylor series only helps when the argument of the cosine is getting close to zero, that's what it is, right? That's what this thing is doing, right? And the argument is getting close to zero. Okay, that's when it comes in handy. And here the argument x, but we have to be careful. Let's go back to our integral. Here our argument x, let me be careful how I'm phrasing this. Okay. Oh, damn it. Let me get this out. Right. So as you can see here, right? Right. As you can notice, right? Because Taylor series only is going to help us when the argument of cosine is going to 0. Here, the argument of x is raised to alpha. Okay. X is raised to alpha. So before using Taylor, okay, we're going to have to ask ourselves something here that are very important, some properties. Okay. So we need to ask what happens. So here's some questions, right? I want to write down some questions we need to ask. So questions. Let's say important question. Question. See, I don't jump right into doing the calculation for this problem. If you do, you're going to be wrong 99% of the time. 99.9 actually. It's not that straightforward. Okay. So the questions that we need to ask ourselves. Okay. What happens? So we're going to say what happens. Even I have to think about this. So what happens? Let me think here. Yeah, what happens? What happens to x? To x? What happens to x as it approaches? It approaches 0. Okay. It's a legit question that you should be asked. That's the first thing that should be coming to your head, right? By common sense. As long as you know how improper integrals work. They work based on the singularities, right? Right. So let me just write here. So as x is approaching, as x approaches 0. Okay, that's what I'm saying here. What happens to x as it approaches 0? Because our integral, right, in the bottom here has a singularity. That's why it's improper, because it blows up. Does that make sense? Okay, so as it approaches 0. Okay. Now, that is the whole problem. That really is the whole problem. If alpha is positive, right? So let's say here, right? So if alpha is positive, that expression will go to 0. So let's go back here. If alpha, right? So going back to our integral, exponent here, x. If alpha, right? If alpha is positive, that expression will go to 0. So number 2, right? Note, this is important. Note. It's jotting important things down. You should do that when you're doing problem solving. If alpha, right? So if alpha, not approaches, if alpha is greater than 0, alpha is greater than 0, right? So if alpha is greater than 0, in other words, positive, that expression, the whole integral, then our integral, then I put it down here, I alpha, right? Let me think about that for a sec. If alpha is going to 0, sorry, if alpha is positive, then our entire expression goes to 0. So I of alpha, which was equal to all of this, right? 1, let me use blue here, blue more. Integral from 0 to 1 of 1 minus cos x to the alpha, all with respect to x over x, right, to the 3 halves, should be approaching 0. Okay, be approaching 0. Right? It has to, right? So I should be saying this is like case 1. Explain here. Okay, so case 1. If alpha is greater than 0, then our integral is approaching 0. Okay, so when alpha is positive, right? Because when if you were to multiply this out and if you integrate, you'll notice that this integral intuitively will approach 0. That singularity there helps. Okay, so that's one thing. Okay, and you'll notice there's cancellations of terms. That's why it's going to be approaching 0. All right. So I want you to think about how I was able to come up at least to case 1, case 2, and so forth. Case 1, anyways. This would be a case 2 for my thinking, anyways. Right? So we have case 1 here, right? For this integral. Okay? Now, I want you to think about this, right? So if alpha is 0, we now want to look at when alpha is 0. Okay? So case 2. Case 2. When alpha, if alpha equals 0. We have to have multiple cases. When you have a variable that they haven't given you any strengths, or that's just arbitrary, you have to come up with cases. Okay? So if alpha is 0, then what happens is, then our I of alpha, right? I of alpha, which is all this, right? So my 1 minus cos x to the alpha with respect to x all over x to the 3/2 is equal to a constant. Okay, so it's equal to some constant. Equals to a constant. Okay, so if alpha is 0, right? Well, if alpha is 0, that means x to the 0, right? So x to the 0 is 1. Cosine of 1 is going to give you a number. And we know if we took integral of 1 minus some number, and you notice that this number here, this number here, when alpha is 0, right? When alpha is 0, cosine of x to the alpha is less than 1. So if cosine, so notice here, cos of x to the alpha is less than 1. So this will be 1 minus a number less than 1. You get a number that's going to be greater than 0. So we'll just say it's a constant. Right? After you integrate that, you know it's going to be a constant. Okay. And if alpha is negative, it blows up. Okay. If you had case 3, right? So case 3, if alpha is less than 0, then you're going to get your I of alpha. Okay. Your I of alpha to be to blow up. Right? So integral 0, 1 cos x to the alpha dx all over x to the 3/2 blows up because of the singularity in the bottom. Okay. But this problem demands a certain split, right? Case by case split. So we're going to try this. Okay. Now I want to mention something about myself. I know I do math problems a lot, but it's related to math problems, and I think it will give you some inspiration based off my own true personal story. I used to get stuck on these types of problems. Hey, even today, if it becomes very complicated, I have to think of it. Mathematics is not easy. Okay, it was never supposed to be easy. I used to get stuck on problems like this too. Okay, not because I couldn't calculate. That's what people don't understand. Mathematics is not about calculation. It's about thinking. It's about problem solving. Thinking and problem solving. Okay. like I knew the formulas, I knew how to calculate things, I knew Taylor expansions. Okay, I knew all like this type of stuff. I knew the formulas, but I wasn't able, right? Um, and I knew the convergence test and all that. But when the exam problem showed up, an exam problem like this showed up, right? Like this, I was freezing up. I didn't know what to do. Okay. I was literally having a problem. Okay? And it don't have to be as difficult as this. Any type of problem that is non-routine, they can just change something a little bit, and all of a sudden you think you knew it, but you actually don't. Okay. Uh, they would add maybe a parameter, they would add some constant, I would freeze up. So what changed everything for me was learning that hard problems are not solved just by guessing. You can't guess your way into this. This is not especially with mathematics. It's not as maybe physics, and even then, it's very hard to do that. But mathematics, there's no hand waving. You have to be very precise. There's no guessing. There's no any of that. So as I said, it changed. Everything changed for me when everything changed for me when it came to learning that hard problems are not solved by guessing. They are broken down using a system, and that system, at least my system, it depends what system you want to use, is this: visualize, model, execute, and verify. This guy right here. I'm pointing on the first page. Okay. That was the step. That was the system. And that system was two teachers who taught me how to use a systems-based technique. Okay. And that changed my life, right? By teaching me how to break down math problems into steps. Okay. That method helped me master actually mathematics and physics. And I earned actually a double major, right? I earned a double major in mathematics and physics at Carleton University. I actually finished with a 3.9 GPA. That's extremely high out of 4. Okay. Uh, and now I use that system to help students. When I graduated university, I said I could have said to myself, maybe get a PhD. I said, no, I don't want to continue with that. I said, why don't I learn the system that my two teachers taught me from high school that helped benefit me in university? And the best way to do that was to start my own coaching company. Right? And I said, I want to help improve people's lives when it came to learning. Okay. All right. So let's get right to it. Step 1, right? You want to visualize. I'm going to do this fast. Okay. So step 1, visualize. Step 1, visualize. Please visualize. Now, I know what you're thinking. Oh, Jason, how are we going to do that? How can you visualize a craziness like this? We're going to visualize this guy here. So first visualize, what I mean visualize in this case, you want to visualize where the danger is, okay? The integral runs from 0 to 1 if you've been paying attention. Okay, so from 0 to 1. Now, yes, it's going from 0 to 1. The denominator becomes dangerous because there's a singularity. What do I mean by that? Well, I mean it approaches 0. Right? That x in the denominator, there is x is going to 0. Because it contains a strong negative power of x. That's why you're having a singularity there, because x is approaching 0. So that's something like based off what you know, you're able to visualize the important thing. Okay. So that's what I mean by visualize in this case. It doesn't always have to mean graphically. Okay. Try to deduce something in your mind. Okay. That makes logical sense. All right. Now, we've got that. Okay. So it's dangerous near 0. At the other endpoint, near 1, nothing dangerous happens. Right? So if we were to evaluate at 0, this will blow up. At 1, nothing will be problematic if I plug 1 into x there. Okay? Absolutely nothing is problematic. Right? Nothing dangerous happens. No singularities. So the entire convergence question is decided near 0. This is a major, major, major breakthrough, a major exam lesson. For improper integrals, do not stare at the whole interval. Okay, I want you to note that, right? For improper integrals, do not stare at the entire integral. Okay, so do not. So for note, for improper integrals, or improper integrals, do not stare at the entire interval, or limits of integration in this case. Okay, entire interval. Please do not do that. It's very important. Find the dangerous endpoint, right? The dangerous endpoint here is at 0, because if you put that limit of integration for all x down here, well, that's where the important things happen. Right here, the dangerous endpoint is 0. So our visual picture is simple, right? If I were to, let's go here, right? I already have a Desmos graph here. All right, so our visual picture is simple. We zoom in near 0. As you can see here, we have our graph for this equation, right? That our improper interval is just a horizontal line right on a y equals 0. Okay, which makes sense because we have then there's a endpoint 0, so the output's to be 0. So we zoom in near 0 and ask whether the numerator is going to decay, if the numerator will decay fast enough. Okay, if I can here, the numerator, this guy here where I'm pointing at, okay, with the laser, if it's going to decay fast enough. Okay, see if it decays fast enough to cancel the singular denominator, right? Because in the denominator, that's our singularity there. When x is 0, denominator. That is the real question. Okay. Now, step 2. So I just wanted to show you how this looks like. Nothing too fancy. Desmos. Okay, let's go back. Step 2 now, we are going to do is model. Step 2, model. Use a different color here. Step 2, model. Okay. So now we model the behavior near 0. There are 3 cases when alpha is positive, right? Case 1, right? So case 1, alpha is greater than 0. Okay, that's case 1. Then the expression inside the cosine becomes very small near 0, right? We talked about that earlier. Okay, this expression, right? The expression inside the cosine becomes very small near 0 when alpha is greater than 0. Becomes very small. So it's like it's approaching 0 because it'll be 1 minus some value of cosine x where alpha is greater than 0. That can include 1. If it includes 1, then that numerator is approaching 0 really fast. Or it can be something else. It can be greater. Alpha can be greater than 1, right? So because it's including alpha greater than 0. Okay. So that's something interesting, right? For case 1, right? So that is the only case where the usual cosine Taylor approximation is valid, actually. So here's a cosine Taylor approximation. Only time when it's valid. The second case is when alpha, right? So case 2. Remember when case 2, when alpha is equal 0. Right, so case 2. Then the expression inside the cosine is just a fixed number. Right? It's going to be some sort of a constant, as we mentioned before. Some sort of fixed number. So the numerator does not shrink near 0, right? Right? It won't shrink near 0 here. Okay? The third, when alpha is negative. Okay, so third, case 3, when alpha is negative, so smaller than 0. Then the expression inside the cosine becomes extremely large near 0. Think about it, right? Just think about it. When alpha is negative, then that would mean that this portion here, right, x to the negative alpha in reality, if alpha is less than 0, that becomes 1 over x to the alpha to make it positive. Okay? Then the expression inside the cosine becomes very large near 0. Because if you have 1 over x to the alpha and alpha is greater than 0, then as alpha is increasing, right, then we would have something of the form 1 over x to the alpha, right? And as alpha is increasing, right, so as alpha increases, then that 1 over x, whatever values it comes out as alpha is increasing, different values of alpha, that portion inside the cosine will get very large near 0. So the numerator is going to oscillate rapidly instead of settling down to 0. Okay, that's the model that we're going to have here. Okay. So the convergence is going to depend, right? The convergence is going to depend whether the numerator gives us enough decay near 0. That's what matters. Positive alpha gives decay, right? 0 alpha gives no decay, right? And that's why my graph here, I didn't let it play. Sort of lazy, probably so. So I don't want to take up too much of your time, but different values of alpha will make this graph oscillate. Okay, that's the point, right? Different values of alpha. Negative alpha gives oscillation without enough decay, and that is pretty much the geometry of the problem. Now let's look at step 3. Okay, so let's look at step 3 now. So step 3, step 3 is a different here, different color. Step 3. Now, step 3, we're going to execute. So, what do I mean by execute? Now we can handle the most important case when alpha is positive. Okay? We're going to look at when alpha is positive. Okay? So when alpha was positive. Okay? So alpha is positive. When alpha is positive, let's go back to our integral here. So when alpha is positive, the inside of the cosine becomes small near 0, of course. Because it's like saying 1 minus cosine of, let's say if we had whatever it is, let's say this whole thing went, x alpha went to 0, cos 0 is 1. 1 minus 1. So you can see that numerator is approaching 0 fast. Right, so it becomes small near 0. Not exactly 0 because it depends on different values of alpha. Let's say if it was x to the 1, x to the 2, x to the 3, then that cosine value can either be greater than 1 or less than 1. So it won't be equal to 0, but it can approach 0. And it will be small difference in variation for 0. So we can use key approximations. Okay. What we can notice is that we have to notice something important here. Notice, I'm going to go to another page. What you want to notice is that 1 minus cosine of a small quantity behaves like 1/2 times the quantity squared. So 1, so notice you're following my reasoning here. Right, so notice that 1 minus cosine of t. I'm replacing x to the alpha with t, okay, just to make things easier for myself. It's completely allowed. 1 minus cosine of a small quantity t behaves, right? It's going to behave actually like 1/2. Behave. I'm going to put an approximation 1/2 of that quantity squared. This is an important approximation. This is an approximation. Okay, sometimes we make approximations in mathematics and science. Okay, so 1 minus cosine of t should be approximately equal to 1/2 of t squared. So what I'm pretty much saying here is the numerator behaves like the square of x raised to the alpha. Square of x raised to the alpha. How do I know that? Like, how am I able to? It's intuitive to think this way. It's not easy. It has to do with sort of connecting to the Taylor series. Notice that this has a relation of x to the 2n. Okay, so I made the relationship with cosine Taylor series x to 2n. Okay, and I came up with noticing a pattern here, right? Pattern of 1/2 the quantity times the quantity squared. Okay, so that's the way you can sort of think about it. It's not easy. Put things in the chat if you have questions, and I will answer them. Okay, after the video, anytime in the video. So the numerator behaves like the square of x. Okay, raised square of x raised alpha. So near 0, the numerator contributes a power of x twice that of alpha. Right. So you can see here, even twice that, the numerator was twice that of the x of the alpha, right? So let's look over here. That's what this guy is doing here. So, and actually, if you substitute cosine of x to the alpha, that's not the main point, but if you substitute that Maclaurin expansion that we have here for cosine, you'll get x to the 2 alpha in your summation, right? So near 0, when we would have to substitute that Taylor expansion here, this guy here, into our integral for cosine, the cosine portion anyways, right? Something interesting will happen. The numerator contributes a power of x to twice that of alpha, and you will see it algebraically. All right? So the denominator is going to contribute a power that behaves like x. Here's the thing, though. The denominator is behaving, if you look carefully, right? The denominator is behaving like x raised to 3/2 in the denominator. Of course, because x to the 3/2. That's my reasoning. So now we're going to use a basic improper integral rule. We're going to notice that a power of x near 0, right? So let's go over here. Notice, so 1, here, 2, right? So notice, so we're going to do this, right? We're going to use the improper integral rule. So we're going to have x, any power of x, x to the power of alpha, right? As it approaches 0, right? It's going to converge exactly. It's going to converge exactly. It's going to converge exactly when the power is not singular. I think that makes sense, right? The power of x near 0 is going to converge. Near, I'm being precise, near 0 is going to converge. If it's exactly at 0, we have a problem. We have a singularity. So it's going to, the power of x near 0 is going to converge exactly when that power is not as, it won't be as singular because it's only singular at x equals 0 in the denominator. So we avoid that paradox, okay? Now, when we applied that rule, the threshold or the reasoning, right, is alpha must be greater than 1/4, right? So number 3, alpha, right? So alpha must be greater than 1/4. Okay. So for positive alpha, right? So for positive alpha, if alpha is greater than 1/4, the integral converges. Okay, let's get back here. So for positive alpha, Just to note, I'm not saying we're in the model stage. I'm just putting all my thoughts organized based on the cases. So if for positive alpha, if alpha is greater than, so for positive alpha, alpha is greater than 1/4, then it converges. So if alpha is greater than 1/4, then it implies I of alpha integral converges. Okay. Now, if alpha is equal to 1/4, the integral behaves like a borderline 1/1 x case, so it will diverge. So if alpha, right? So if alpha is equal to 1/4, right? So if alpha equals 1/4, will imply that I of alpha that would diverge. I won't go into it. I only have so much time. You can ask me questions in the chat. Okay. And you can verify the math too if you want for homework. So it diverges. Now, if alpha is positive but less than 1/4, so if alpha is positive but less than 1/4, what do you think will happen? Singularity is going to make it diverge. It diverges again. So only when alpha is greater than 1/4 for when alpha is greater than 0. So when alpha is greater than 0, only in the case when alpha is greater than 1/4, our integral will converge. Okay. So that's the main answer. Okay. But we still have another case, and that case is our execute case. Okay. We have to execute when alpha equals 0. Okay. So when alpha equals 0. All right. So when alpha equals 0 in our integral. Okay. So suppose when alpha is 0, then x is raised to alpha is just 1. Obviously, alpha is 0, this is the easiest part. X to the 0 is 1, 1 minus 1 is 0. Then x is just raised to just 1. Raised alpha is just 1. So the numerator becomes a constant. 1 minus, cosine of 1. Okay, that number is positive. I think that's pretty self-explanatory. So near 0, the integrand behaves like a positive constant divided by x to the 3/2. That is 2 singular near 0, right? I think you can agree with that. This case is important because most students will try to force the positive alpha, that positive alpha here, okay, that positive alpha, Maclaurin type of logic into alpha equals 0. But that's going to be wrong. That's going to be plain wrong. When alpha equals 0, the cosine argument goes to 0. Does not go to 0, sorry. No, it does not go to 0. Right? When alpha goes to 0, be careful. This is what trips people up. When alpha goes to 0, so that's x to the 0 is 1, that's cosine of 1. So 1 minus cosine of 1, not 1 minus cosine of 0. 1 minus cosine of 1. So when alpha goes to 0, the cosine argument does not go to 0. Be careful, that's cosine of 1. So the Taylor approximation near 0, referring back to Taylor, this guy here, Taylor approximation near 0, and it is near 0. Remember, Taylor approximation is used when we approach something. It's near 0 because it's x minus a here, normally for Maclaurin. I mean for Taylor, but a is 0 here. Right? You'll notice here, right? When alpha equals 0, the cosine argument does not go to 0. Right? So the Taylor approximation near 0 is going to be the right approach. Okay? Right? So still part of the execute phase. Okay? Still part of the execute phase here. It's a bit extended. This would be like a step 4 or 5 here, but the reason why normally my method is from 1 to 4, right? Steps, but I had to extend the steps here because of the fact that we have multiple cases in our execute phase. So it's like a step 5 here. Okay, I'm not going to write that down. So let's suppose if alpha is negative. That's what I mean. Alpha is less than 0. That is the case that often confuses students the most. When alpha is negative, x raised to the alpha blows up as x approaches 0. So the expression inside the cosine does not become small, it just becomes very large. Right? I think you can agree with that. This expression here is going to become large, very large. That means the numerator will keep oscillating. Okay, so not a constant amplitude in the periodic function, but it will oscillate with different amplitude. Okay, it's going to just keep oscillating. Now, oscillations alone does not automatically save an improper interval. That's the main point. That's a huge point. The numerator is 1 minus cosine, so it's always going to be non-negative, right? It'll always be non-negative. 1 minus cosine x to the alpha, non-negative. It repeatedly gets close to 0, but it also repeatedly becomes substantially positive because it's greater than 0. Okay? So there are infinitely many intervals near 0 when the numerator is not small. Infinitely many. On those intervals, the denominator is extremely singular, of course, because you have the x to the 3 halves. That's two singularities. So the integral accumulates too much positive area. Right? We had a graph here, too much positive area. It's not going to be exact, but if you were to look at a cosine curve, it'd be too much positive area. I mean, like up here. Correct me for my graph, and it's not accurate whatsoever, but my point is to show you some sort of cosine curve where the area A, right, is too much positive area. Therefore, for negative alpha, if you had negative alpha, the integral will diverge. That's pretty much the short version. I hope you understand the logic of that. So without the k, the denominator wins. So a negative alpha doesn't work at all. It's pointless. Okay. Now, if you wanted to verify this, right? If you want to verify our little friend here, right? All this, for verify, we're in mathematics, we have to verify arguments. For verify. Okay. We can verify this. We checked every possible type of alpha, which is true. Positive, 0 alpha, negative alpha. For positive alpha, convergence happens, right? For positive alpha, we had that convergence happens. Only when the alpha is greater than 1/4. At alpha equal to 1/4, the integral hits exactly the borderline and diverged. Okay. For alpha less than 1/4, remember, if alpha is less than 1/4, right? So for alpha, let me think here. Yeah, alpha less than 1/4, which is still a part of 0, including the 0, right? All negative values, the integral diverges. So our final result is that the integral converges exactly when alpha is greater than 1/4. So when alpha is greater than 1/4, the integral converges absolutely. Okay. So when alpha is greater than 1/4, then it automatically implies that our integral I of alpha, which is equal to the integral from 0 to 1 of 1 minus cosine of x to the alpha, on parentheses dx all over x to the 3 halves, converges absolutely. Converges absolutely. So our value for this problem is alpha has to be greater than 1/4. And that is it. Okay, if you felt intimidated by that, that's okay. Very, very few people get a problem like this. But I wanted to show it to you, right? I wanted to, yeah, I just wanted to show it to you guys to show that problems like this can happen. They're rare, but if you can think like this, your mathematics is going to be fine in any course you do in university. Okay. All right. So the big point here, here's the real lesson to this lesson today. And it was a long lesson. I didn't expect it to be this long, but the problem is hard. So this problem is not testing whether you know cosine or Taylor, right? Cosine, Taylor series, or what an improper integral is, or whatever. It is testing whether you know when you're allowed to use expansion, and if you could put uh, multiple different concepts together in the same course. That's what it's testing. And that's a much deeper skill. It is a skill in itself. The mistake is saying, "Oh, I see cosine, therefore Taylor." No, that's if you just did that and expanded out, you're wrong. The correct reasoning is the argument of the cosine approaches zero only when alpha is positive. So Taylor only belongs in that case. Okay, that is why this is a hard example, a problem, because it forces you to think beyond computing, beyond calculating. Okay, that's how a scary dependent improper integral actually becomes manageable, in my opinion. I don't know how manageable it was for you. um, but yes, if this problem felt overwhelming at first, that does not mean you're bad at calculus, not even close. Okay, it means the problem hid the real decision-making variables. Most students try to calculate right away. If you calculate right away, not just for this problem, even easier problems, but it could be easier problems and still be hard, you'll get it wrong. You have to set up your thinking correctly. That's what you want to do. Okay, you have to have a systems approach for thinking. Right, so most students can be too early, but hard calculus problems usually reward students who pause, think, and ask. Right, ask questions. What behavior controls the problem? Here, the behavior is at the endpoint of. Here, the behavior is the endpoint near zero. Right. That's what you want to focus here. All the important things that you know about improper integrals, singularities, endpoints, that type of stuff. And also that the controlling parameter is alpha. So once you see that, the problem is going to become much less complicated. And that's exactly why I teach students my system. You don't need to magically guess the answer. You don't need to, and you don't need to be a genius to do math. You just need a correct method. Okay? Not to say that math isn't hard, it is, but it's not only to an exclusive group only. Right? So if you understand lessons, okay, if you understand lessons in the class, but freeze up when you have uh, a specialized problem like this, or an exam question that adds a parameter, this is exactly what I help students fix. I teach hard calculus problems using my visualize, model, execute, and verify method. You can also download my guide, my 7 hard calculus exam tips. They'll be in the link below in the script of the video. And it's going to show the exact mistakes students make on hard exam questions and how to fix them early on. So that link will be in the description below. And if you want help applying this system to your own midterm or final exam prep or any other course material, uh, I have my own personalized coaching lessons. I've designed a curriculum to help you be able to solve hard problems like this. Coaching link will be in the link below of the description. Comment Exponent if you want more hard improper integral problems. I like getting feedback from you guys. It really helps. And that is it. I'm going to be posting another video this week. So there might be 2 more, depending on how much time I have. I'm probably going to try to do 2 more videos this week. Okay. It's always a pleasure, guys. Stay tuned for more. They get more interesting. Bye bye.